Hello everyone and welcome to the coronavirus edition of the Signal Theory class. This is the first lecture, so we will have to go through some basic stuff which is a bit boring, but it is necessary to get some basics out of the way. Okay, so first we will talk about the classification of signals and systems. First, we can classify both signals and systems as either continuous time or discrete time. The continuous time signals are essentially functions defined on real numbers, which usually represent time, and their values can be real or complex numbers. So when you plot a continuous time signal, it can look like this: a real function of a real variable. In contrast, the discrete time signals are functions of integers, which usually represent discrete time, that means values 1, 2, 3, 4, 5, 6, and so on, and the values of the discrete signals can again be real or complex. So when you plot a discrete time signal, you will get a sequence of values like this one. Note that I'm using different notation for continuous time signals and for discrete time signals. The continuous time signals have their argument in round brackets, and the discrete time signals have their argument in square brackets. Now, regarding the systems, the continuous time system is the one which operates on the continuous time signals, and the discrete time system is the one which operates on the discrete time signals. Now, there is another distinction that we can make, and we can classify the signals and systems into deterministic and stochastic. To give you an example of a deterministic system, imagine a box which has a start button, and each time you press that start button, this system will generate a signal. If this system is deterministic, this generated signal will be the same each time, every time. In contrast, in stochastic system, pressing this start button can generate a slightly different signal each time. A real-world example of a stochastic system is you when I step on your foot. Each time I step on your foot, which is equivalent of pressing the start button, you will generate an ouch sound. But you will never say the same ouch twice. So each time I step on your foot, you will generate a slightly different signal. Thus, you are a stochastic system. In contrast, an example of a deterministic system would be a system the output of which would be described by a mathematical function. For example, if the output of this system is described as sine of t, the output will be the same each time, every time. Thus, you are dealing with a deterministic system. Now, the output of a deterministic system is a deterministic signal, and the output of a stochastic system is a stochastic signal. And these individual measurements of the stochastic signal are called realizations. And in case of the stochastic system, these individual realizations are different. In the case of the deterministic system, each realization is the same. Now, all the real-world signals and systems are stochastic. Even if you have a function generator which is supposed to generate a sine wave, that sine wave will have some noise in it. So each time you turn that function generator on, it will generate a slightly different signal. So all the real-world signals and systems are stochastic. However, the stochastic signals and systems are kind of difficult to deal with. So in practice, what we often do, we approximate them with a deterministic system, which is easier to analyze and synthesize. And that is what we will do in this course. We will deal with deterministic systems only. In some subsequent courses, you may learn how to deal with stochastic systems and signals. Another classification that we can make is to differentiate between the periodic and aperiodic signals. And you probably know this, the periodic signals are the ones which repeat themselves. There is this interval which is called period, and this interval has length of t, which is also called a period. And when we take the signal at time t and shift that time by the period, we will get the same value. So that signal repeats itself with the period. 1 over t, 1 over period, is the frequency of the signal. What students sometimes do not know is that this is not the only period of the signal. Yes, this interval repeats itself, but this interval also repeats itself, and this interval also repeats itself. So when t is the period, 2t, 3t, 4t, and so on are also periods of the signal. The smallest period has a special name, and we call it the fundamental period. In contrast to a periodic signal, we have a periodic signal, which simply does not repeat itself. Another type of properties of systems I want to mention is time invariance and linearity. Right now, these properties may appear a little bit abstract, and it may not be completely clear to you why we care about them. The usefulness of these properties will become clear later. At this point, I'm including them just for completeness. So right now, just try to understand the basic principle, and later I will come back to this and you will see what it is good for. So first, the time invariance. Let's say we have a system and we feed this system some input signal u of t, and this input signal u of t will create the output signal y of t. Now, this system will be time invariant if, when we shift the input signal by some amount of tau, we will get the same output signal except shifted by the same amount of tau. Essentially, that means that this system does not change its properties in time. When I feed it one signal today, I will get some output, and when I feed it the same signal tomorrow, I will get the same output. If this does not hold, we call this system time variant. That means that this system changes its properties in time. When I feed it one signal today, I will get one output, but when I feed it the same signal tomorrow, I would get a different output. Now, linearity. Let's have a system. When I feed this system signal u sub 1 of t, I will get some output y sub 1 of t. When I feed the system u sub 2 of t, I will get a different output y sub 2 of t. Now, the linearity of this system will depend on what happens when I feed the system this combination of these two inputs. Here, these two signals are multiplied by constants a and b, and then they are summed together. This combination we call a linear combination. Now, when I feed this linear combination to my system and I will get the same linear combination of the outputs, we say that the system is linear. Again, this may sound a bit abstract. Now just take it as a fact and later you will understand it better. Now, sometimes we have systems that are both time invariant and linear. Those we call linear time invariant or LTI systems. The nice thing about LTI systems is that they are relatively easy to analyze and synthesize. In fact, most of the systems that we will deal with in this course will be LTI systems. And if those systems are not linear, then we will try to approximate them by a linear system using a process called linearization. So in the future, you will learn to like LTI systems, and then you will appreciate their definition. Yet another way how to classify systems is to distinguish between stable systems and unstable systems. First, I will illustrate on some examples. Here I have an example of a stable system. It is a pendulum that is fixed at this point, and here is some mass that can swing back and forth. In real life, this swinging will not continue indefinitely, but the pendulum will slow down and it will come to this stable point. When I plot the angle of the pendulum over time, I can get something like this. As time goes to infinity, the angle will asymptotically approach zero, so this system is stable at this point. In contrast, here I have an example of an unstable system. Here I still have a pendulum, but now it is turned upside down. This is what we call an inverse pendulum. Now the pendulum is fixed at this point, the mass is here, and now the mass can swing back and forth like this. However, it will not swing back and forth in any periodic fashion. If this angle deviates from the vertical position by the smallest amount, this inverse pendulum will simply fall to a side. When I plotted the time course of the angle of the pendulum, I can get something like this. The system does not converge to this point, it runs away from it, so this system is unstable at this point. Mathematically, we have several definitions of stability. A system is Lyapunov stable if it remains within some deviation of the equilibrium if it is started close enough to that equilibrium. So if I have some equilibrium point and I will set some limits, some deviation plus and minus epsilon from that equilibrium point, then the system is Lyapunov stable if it remains within these limits when it is started close enough to the equilibrium point. A system is asymptotically stable if it not only remains close enough to the equilibrium point, but it also asymptotically approaches the equilibrium. That is, for time going to infinity, the system will approach the equilibrium point. When you plot the behavior of such system, it will approach that equilibrium point as time goes to infinity. A system is exponentially stable if it has asymptotic stability, and on top of that it converges to that equilibrium faster than some exponential. So if your system converges to its equilibrium faster than any exponential, you can say that it is exponentially stable. Now, all these definitions of stability are often applied to all the variables in the system, even the internal ones which we cannot see. In contrast to that, there is definition of stability which is called bounded input, bounded output stability, and that is concerned only with inputs and outputs of the system. If the system is BIBO stable, then when the input of the system is bounded, that is finite, the output of the system is bounded, that is finite. So BIBO stable system reacts to finite inputs with finite outputs. The BIBO stability does not say anything about what's going on inside a system. So you can have a system which is BIBO stable, but it still has some internal variable, some internal state that diverges to infinity, in which case it would not be internally stable according to these previous definitions. Now, all of this is a bit abstract, so before I continue, I will show you a small demonstration where you will see stable and unstable behavior of a system, and also I will demonstrate some typical behaviors which will then guide us to the signals that are needed to describe them. Now, this is a pendulum. If you take a pendulum and turn it upside down, you will get an inverse pendulum. Not surprisingly, the inverse pendulum is not stable at this upright position. That is, unless you put a stepper motor at the bottom and a regulator on the top, in which case you can make even the inverse pendulum stable. Here I will demonstrate the stability of the inverse pendulum by pushing it and letting it return to its stable position. Now I also have a wireless link to this pendulum, so for example I can move it back and forth. But more importantly than moving the pendulum back and forth, I can change the setup of the regulator on the top of the pendulum, and that will allow me to demonstrate different types of behavior. Right now I have my pendulum up and standing, but I have screwed up the setup of the regulator a little bit, so when I push the pendulum now, it will come back to the stable position, but it will do it in this rocky motion. If you design a regulator, this is probably not what you want, but this is a behavior a system can manifest. Right now the pendulum is set so that it is nicely stable, but if I screw up the setup of the regulator, which I have done just now, the pendulum will become unstable, it will run away to one side and then it will fall. Here the pendulum is standing again, but right now I have screwed up the setup of the regulator so that it will become unstable, but this time it will do it with this rocky motion that just keeps bigger and bigger. So these are some very basic types of behavior we will see in simple systems. Sometimes the systems will be stable, sometimes the systems will be unstable, and sometimes the systems will come to their equilibrium in that smooth exponential fashion, and sometimes the motion will be rocky. In the previous demonstration, you have seen that the inverse pendulum can manifest these types of behavior. It can come to its equilibrium position in this smooth fashion, or it can become unstable and run away to one side. Also, you have seen that the inverse pendulum can come to its stable position in this rocky fashion, or it can start to rock like this and become unstable. Now, if you did the appropriate math, you would find that this motion could be described with a decreasing exponential. Also, this motion could be described by an increasing exponential. This motion could be described by an exponentially damped sine or cosine, and this motion can be described by an exponentially amplified sine or cosine. In case of the inverse pendulum, these descriptions are a little bit approximate because the inverse pendulum in its upright position is a little bit nonlinear. But when you are dealing with a system that is completely linear and time invariant, its behavior can often be described exactly using exponentials, sines and cosines. And that is also why we like those LTI systems, because their behavior can be described relatively easily. Now, to make sure that you will be able to describe the behavior of those LTI systems, at the risk of being boring, on the following slides I will go through those exponential sines and cosines. So first, the real exponential. Mathematically, we can write the real exponential like this, and its graph looks like this. Important point to note is that depending on this sigma, the exponential can asymptotically approach 0, which happens when sigma is negative, or it can diverge to infinity, which happens when sigma is positive. So based on the value of sigma, we will be able to distinguish between these two types of behavior, between the stable and unstable behavior. Now, sine and cosine. We typically work with sines and cosines in this form. This is the amplitude, this is the frequency, and this is the phase. We often denote 2 pi f as omega, and we call that the angular frequency. When you plot the cosine, you will get something like this. This will be the period of the cosine, which is 1 over the frequency. This is the phase of the cosine, and this is the amplitude. Hopefully everybody knows this. What you may not know are a few details about a discrete sine or cosine. In the discrete world, we use sine and cosine in this form. It's kind of similar to this one. We have the amplitude and we have the phase. The change is that here, instead of the angular frequency, we have this capital omega, which we call the normalized frequency. And a fun fact about discrete cosine is that it does not have to be periodic. For example, when this omega is 1 and you have cosine of n, you could check that the values of this cosine do not repeat themselves with any period. So a discrete sine or cosine does not have to be periodic. Now, damped sine and cosine. You have seen these types of behavior with the inverse pendulum, and this can be described by taking a cosine or a sine and multiplying it with an exponential. And depending on the value of this sigma, you will get exponentially damped sine or cosine, which happens when sigma is negative, or exponentially amplified sine or cosine, which happens when sigma is positive. So depending on the value of this sigma, we will be able to distinguish whether we are dealing with stable or unstable behavior. Few students have problem with sines, cosines or real exponentials, but what a lot of students do have problem with is the complex exponential. So let me explain that. When we have a pendulum, you can imagine that its behavior can be described like this. Mathematically, you can write that motion using this expression for the damped cosine. However, when I teach you the techniques that will allow you to describe the behavior of LTI systems analytically, you will find that the solution is often not presented to you in this clear form, but in this cryptic form that uses complex exponentials. Instead of a sine or a cosine, we'll get two complex exponentials where this a will be a complex number and this s will also be a complex number. And of course, you also need to understand this cryptic form of writing sines and cosines, so I will need to explain that complex exponential. So, the complex exponential. Mathematically, the complex exponential can be written in a very similar way to the real exponential, except now this a is complex and we call it the complex amplitude, and this s is also complex and we call it the complex frequency. Typically, we write the complex amplitude in the polar form, where the magnitude of the complex number will correspond to the amplitude of the sines and cosines hidden in the complex exponential, and the phase of this complex number will correspond to the phase of those sines and cosines hidden in that complex exponential. The complex frequency is often written in the rectangular form, and the real part, this sigma, corresponds to the damping of sines and cosines hidden in here, and the imaginary part, this omega, corresponds to the angular frequency of the sines and cosines hidden in this complex exponential. Now I will first demonstrate mathematically how to find sines and cosines in the complex exponential, and then I will illustrate it on some pictures. So first the math. When I write down the complex exponential, I can substitute this expression for the complex amplitude and this expression for the complex frequency. When I do that, I will get this. Here I can break this exponential into these two exponentials. That will give me this. Here I can combine these two exponentials into this single exponential, and that will give me this. Now, using the Euler's formula, I can write this exponential as a sum of a cosine plus j times sine. So I will get this expression. Now when I multiply both cosine and sine by this expression, I will get this. And here you can see that the real part of this complex number is a damped cosine, and the imaginary part of this complex number is a damped sine. And this omega will determine the angular frequency of this cosine and this sine. This sigma will determine the damping of this cosine and sine, and this amplitude will determine the amplitude of this cosine and sine, and last, this phase will determine the phase of this cosine and sine. So the complex exponential hides cosine and sine in its real and imaginary part, and the complex amplitude and the complex frequency determine the parameters of this cosine and sine. Now let me show you how you can visualize the complex exponential. First, let me remind you how you can visualize a complex number. Here I have a complex plane. This is the real axis and this is the imaginary axis. This is my complex number A. This distance is the magnitude of the complex number, and this angle is the phase of the complex number. This is the real part of the complex number, and this is the imaginary part of the complex number. When I know the magnitude and the phase, I can write that the real part of the complex number is the magnitude times the cosine of the phase. And I can write that the imaginary part of the complex number is j times magnitude times the sine of the phase. With this, I can write that complex number in the polar form and in the rectangular form. In that rectangular form, we have cosine and sine of the phase of the complex number. Now, this is not yet the complex exponential from the previous slide. To get that complex exponential, we need to add some changes. And first, we will change the phase of the complex number like this. We will add this term omega times t, so that at time 0 the phase of this complex number will be phi, and then as time rises, so will the phase of this complex number. In fact, this is no longer a single complex number, this is a function of time. So this is a signal which I will denote as x of t. This is how you can visualize it. My signal x at time 0 will be at this point, and this phase is phi. Then, as time rises, so will the phase of the value of my complex signal. So as the time rises, the value of my signal will move along this circle like this. And when I want to express the real part of my signal, I can write it like this. It's the magnitude times the cosine of the omega t plus phi. And when I want to express the imaginary part of my signal, I can write it as j times the magnitude times the sine of omega t plus phi. So using this, I can write my signal in this polar form or in this rectangular form. And in this rectangular form, the real part contains a cosine and the imaginary part contains a sine. This signal actually already is a complex exponential, but here the cosine and sine have constant amplitude and we do not have any way how to make it increase or decrease over time. To get a more general damped cosine or sine, we need to take this term and add this exponential damping. The visualization of this term will be similar to this case, however now the magnitude, this magnitude will not be constant. Take a look at here. The magnitude is being multiplied by this real exponential, which can make it bigger or smaller. So this magnitude, if sigma is negative, will get smaller over time. So the movement of the value of my signal in the complex plane will no longer follow a circle, but it will be a spiral. Now the real and imaginary part of my signal will be similar to this case, except now this cosine and this sine will be multiplied by this exponential and this exponential. And this is the complex exponential that I showed you on the previous slide. In the previous slide, I showed you the complex exponential in this form, but here I will show you that this form and this form are equivalent. So I will take this, I will write it here, and now I will break this exponential into these two exponentials. Now I will rearrange the order of these three exponentials, and that will give me this. Here I can combine these two exponentials into a single exponential, which will give me this. And here I will denote this as complex frequency S, and I will denote this complex number as the complex amplitude A, and that will give me that complex exponential which I showed you on the previous slide. So this complex exponential is a signal, the value of which is following a spiral in the complex plane. And the real part and imaginary part of this signal are damped cosine and sine. Also, the parameters of this damped cosine and sine are hidden in this complex amplitude and complex frequency. The complex amplitude, that is this complex number, will give you the real amplitude of the cosine and sine, and it will also give you the phase of the cosine and sine. And the complex frequency, that is this complex number, will give you how much the cosine and sine is being damped, and it will also give you the angular frequency of the cosine and sine. Now let's get back to the original motivation which I used to start talking about complex exponentials. I told you that oftentimes you can describe a behavior of a system using a damped cosine or a sine. And also I told you that those analytical tools that we will learn in the future will not give you the behavior of the system in this form, but they will give you the behavior of the system in this cryptic form using complex exponentials. In the previous slides, I showed you that a complex exponential contains both damped cosine and damped sine. But how do you take two exponentials and combine them to get a single damped cosine or a sine? Well, that is what I'm explaining in this slide. I will start with cosine. I would like to find a way how to express a cosine using two complex exponentials. This is how I can do it. I can take this complex exponential, e to the j phi, that is this complex number, and to this complex number I will add its complex conjugate, that is e to the minus j phi. Now, two complex numbers are added like vectors. So when I add this complex number to this complex number, this will be the result. Now, what is the value of this result? Well, its imaginary value is 0, so it's going to be a real number. And what is its real value? Well, it's going to be twice this value. And what is this value? Well, that is the real part of this complex exponential, and that is cosine of phi. So this is going to be 2 times cosine of phi. So when I add this complex exponential and this complex exponential, I will get 2 times cosine of phi. Here you have it written down mathematically. This complex exponential plus this complex exponential is 2 times cosine of phi. So if I want to express cosine of phi, I need to take these two complex exponentials and divide them by 2. So this is how I express cosine of phi using complex exponentials. Now, what about a sine? This is how you do a sine. You will take this complex exponential, e to the j phi, then you will take its complex conjugate, which is e to the minus j phi, and then you put minus sign in front of this complex number. That will give you this point. This is minus e to the minus j phi. And now you will add this complex number and this complex number. Again, those complex numbers are added like vectors, so when you add this and this, you will get this point. This point has 0 real value, it is purely imaginary. And what is its imaginary value? Well, it is twice this value. And this is the imaginary value of this complex number, and that is j times sine of phi. So this point will be j 2 times sine of phi. Here you have it written down mathematically. When you take e to the j phi and you subtract e to the minus j phi, you will get j 2 times sine of phi. So when you want to express sine using complex exponentials, you need to divide this expression by 2j, and that is written here. This is how, using complex exponentials, you can express a sine. Now, what about a generic cosine with some generic amplitude, angular frequency, and phase? Well, here you can still use this expression, except instead of this phase, you will use this entire expression. And when you substitute this here and here, you will get this. In this expression, you can break each of these exponentials into 2 exponentials, and then you can rewrite this entire expression into this form. Here you can denote this as complex number a and this as complex number a conjugate. When you do that, you can write this entire expression in this form. And this is how you can express a cosine with some generic amplitude, frequency, and phase using 2 complex exponentials. Now, what about a damped cosine? Well, you can do pretty much the same thing. You will still use this formula, and for this phi and this phi you will substitute this. When you do that, you will get this expression, and here again you can break this exponential and this exponential into 2 exponentials in the same fashion as we did it here. Then you can rewrite this expression into this one. And here you can denote this complex number as a, and this complex number will be a conjugate. Moreover, you can combine these 2 exponentials into a single exponential and these 2 exponentials into a single exponential. And you can denote this sigma plus j omega as complex frequency s, and this as minus j omega as complex frequency s conjugate. And when you do that, you can write this expression in this form. And this is how you can combine 2 complex exponentials to create a general damped cosine. Now, if you wanted to express a general damped sine, this is a derivation which can show you that you need to use this formula. It is very similar to this one, except instead of this plus you will use minus, and instead of these 2 you will be dividing by 2j. In this slide, I will tell you about the Dirac delta function. The Dirac delta function is an object that is used in many fields for many purposes, and we will use it, for example, to examine the properties of a system. The Dirac delta function has this interesting property that as a signal it contains all the frequencies. It contains low frequencies, mid frequencies and high frequencies. So when we feed it into a system and we take a look at the output of the system, we can examine how the system behaves at different frequencies. But that is what we will do in the future. Right now I will just tell you what the Dirac delta function is, and I will tell you about a few of its properties. First, the Dirac delta function is actually not a function. In fact, it is so-called generalized function, and this is how we can describe it. I will start with a signal in the shape of a pulse, and I will denote this signal as d of t. This pulse has a width of delta and height of 1 over delta. When you define a pulse like this, the area under the pulse will always be 1 because it is given as delta times 1 over delta. Therefore, mathematically we can write that the integral of this function d, that is of this pulse, is always equal to 1. Now, this is not yet the Dirac delta function, but this will become the Dirac delta function when this delta in limit approaches to 0. When this delta approaches to 0, this pulse will become infinitely narrow and also infinitely tall. So when I take this pulse of ours and I will limit delta to 0, I will get the Dirac delta function, which I will denote as delta of t, and I will plot it as an arrow pointing upwards. So informally, you can imagine the Dirac delta pulse as infinitely narrow and infinitely tall pulse. Also, you can imagine it as a function which is 0 everywhere, except for time is equal to 0, it is infinite. But these are only informal description. Formally, working with Dirac delta function means taking this pulse and sending in limit this delta to 0. Now, one very important property of the Dirac delta function is that the area under the Dirac delta function is always 1. Why do we get it? Well, it should be pretty obvious. The area under this pulse is always 1 and it doesn't depend on delta. Mathematically, this integral is always 1 and it doesn't depend on delta. Therefore, when delta limits to 0, the area under the pulse will not change. The area under the Dirac delta pulse will not change. Therefore, this integral is always 1. Remember this, we will use it a lot. Another thing that we will use quite a bit is so-called sampling property of the Dirac delta function. It's quite simple, so I will show it to you right now and you will be ready for it. Okay, so let's have some function f of t and let's have a Dirac delta function which is shifted to the time t0, time t0. And now let's multiply that function f of t by that shifted Dirac delta function. And let's take this integral of this expression. We will see this kind of expression quite a bit, so we should learn how to evaluate it. To do that, we first need to realize that the Dirac delta function is 0 everywhere except at t0, where we can imagine that it goes to infinity. That means that when I multiply this Dirac delta function with this function f of t, the values of the function f of t will not matter in most of the points because they are being multiplied by 0. The only exception is at time t0. So I can pretty much forget about all the values of the function f of t, and I can use only the value of the function f of t at time t0. And that is what I'm doing here. Instead of this expression, where I have the entire function f of t, I'm just using the value of the function f of t at time t0. And when I do this, I can realize that this is just a constant, so I can take it in front of the integral, which will give me this. And here I will use the fact that the area under the Dirac delta function, that is this, is always equal to 1. So this integral is always equal to 1, thus this entire expression will be just f of t at time t0. So when I take a function and multiply it with a Dirac delta pulse time shifted to time t0 and I take this integral, what I will get will be the value of the function at time t0. So basically this expression will sample my function at time t0, at time t0. Thus, this property of the Dirac delta function is called the sampling property of the Dirac delta function. Now, I understand that this may appear just like an abstract math to you, but we will use it a bit, so learn it and it will make it easier for you when we use it in some applications. The last thing I want to show you in this slide is the discrete Dirac delta function. Sometimes we just call it the unit pulse. It is a very simple function. It is 1 when n is equal to 0 and it is 0 otherwise. This is how you write it mathematically. The discrete Dirac delta function is 1 when n is equal to 0 and it is 0 otherwise. In this slide I will tell you about the unit step. Sometimes we also call it the Heaviside step function. And it is a fairly simple function. It is 0 for negative time and 1 for positive time. The value for 0 time is most often defined as 1/2. So this is how you can write it mathematically. The unit step is 1 for positive time, 1/2 for 0 time, and it is 0 otherwise. This is how the unit step is connected to the Dirac delta function. When you take the integral from minus infinity to t from the Dirac delta function, you will get unit step. This is actually no rocket science. When you integrate the Dirac delta function from minus infinity to some negative time, you are integrating only 0, so you will get 0. So for negative time, you will get zeros. When this time is positive, then you will integrate from minus infinity to some positive time, which will include this Dirac delta pulse, and that integral will be 1. For positive time, you will get 1. When this time is equal to 0, this is a bit tricky. To do it properly, you need to go back to the definition of the Dirac delta pulse, and you realize that in this case you are including only half of this pulse. And that is the reason why when this time is equal to 0, this integral is equal to 1/2. And that is of course equal to the definition of the unit pulse, which for 0 time is equal to 1/2. The main point to remember is that this integral of the Dirac delta pulse is equal to the unit step. Now, this is not the only definition of the unit step out there. Sometimes you can see the unit step defined like this. It is the same as here, except at 0 the unit step is 1. So the unit step in this case would be 1 for 0 and positive time, and it would be 0 otherwise. Yet another, a bit more complicated definition of the unit step which you can see is this. First you define this function u, which is almost a unit step. It is a 0 for the time which is less than some minus delta over 2, and it is 1 for time which is more than some delta over 2. And when you have this function defined, you will take delta and you will send it to 0. That will turn the function u of t into the unit step. This is a similar limiting process that we use to define the Dirac delta function. Of course, the question is why to go into all of this trouble? Well, it does have one advantage. When you define the unit step like this, you can actually say that the derivative of the unit step is the Dirac delta function. Why is that? Well, when you take derivative of this function u, you will actually get this function d that we use to define the Dirac delta function. Let's take a look at it. Here the derivative would be 0, so here you have 0. Here the derivative would be 1 over delta, and here you have 1 over delta. And of course here the derivative would be 0, and here you have 0. So you can write that derivative of the function u of this function is function d, that is this function. And now when you take delta to 0, this expression will turn into this one. The derivative of the unit step is the Dirac delta function. Note that this is pretty much inverse to what we have here. Last, this is the definition of the discrete unit step. It's very simple. It is 0 for negative values of n, and it is 1 for positive values of n. So this is how you can write it mathematically. The discrete unit step is 1 for positive values of n, and it is 0 otherwise. Similar to this expression, here we can write that when we take the sum from minus infinity to m of the discrete Dirac delta pulse, we will get the unit step. Again, it makes sense. When I take the discrete Dirac delta pulse and I will sum its values from minus infinity to some negative value of m, I will sum only these zeros. So for negative value of m, this sum will be 0 as it should be. Now, if this m is positive, this summation integral will include this one, and that means that this sum will be equal to 1. So if this m is positive, then this sum is equal to 1 as it should be.